All right, mathletes, here's 2.1, functions and domain. Some vocab we need here to understand is first, function is a relation where each input has exactly one output. In other words, we only want one answer. We cannot have two answers with a function. Next is domain. It's a set of all inputs of a function. Typically, we think of inputs as x values, and we think of our output as our y values. Okay, and the range is a set of outputs of the function. All right, so how do you know if a relation represents a function? Well, you need to understand that if you think about it graphically, it must pass the vertical line test. In other words, if you lay a vertical line anywhere on a graph, it can only pass over one single point. Because if it passes over 2 points, okay, you have some x values the same, let's say 2, and you have some y value here, which is maybe 0, and another y value of 10. And you can see that the input of 2 has two solutions, 0 and 10. That is not a function. So a vertical line test, a function must pass a vertical line test, meaning it can only cross once. If it crosses more than once, it is not a function. Okay, so number 2, does 3, 5, 4, 2, 1, negative 1, 0, negative 2, 2 represent a function? Well, you can graph these points, and so we have negative 3, 5, we have 4, 2, we have negative 1, 0, and negative 2, 2. Notice if I have any vertical line and I drag it across my graph, it's only going to pass, make it thinner here, we only have one point that it ever crosses. Okay, so yes, it is a function, and it's because every input has a unique output. Okay, so part 2, if we look at and graph these, we have 2, 3, we have 5, negative 1, we have 2, 6, and we have 0, negative 7. Okay, so we can see here at 2 we have an issue. It does not pass the vertical line test. At 2 we have two answers, one being 3 and one being 6. So this is not a function. Because 2 as our input has two different outputs. Okay, so for number 2, to state the domain and range, well, my domain, so notation is going to be important with this, domain is for all, so the domains of this is my x values. So I can do this in set notation. So I usually like to start with the smallest one, negative 2, negative 1, 3, and 4. All right, and then my range is the possible outputs, my y values. So notice that my y value repeated here. Okay, it was fine that when we graphed them, it didn't pass a horizontal line test, but it still represents a function. Because it repeats itself twice, I don't need to write it twice, but I can just write it as 0, 2, and 5 for my y values or my ranges of that function. All right, so determine whether each equation is a function. If it is, give the domain. If it isn't, explain why. Well, y equals 5x, any number I can multiply by 5 and add 3 to it. Okay, and every time I'm going to get a different answer. Okay, if I make a graph of that, I can see that y equals 5x plus 3 will pass the vertical line test and will never cross more than once. So it is a function. And my domain, I'm going to abbreviate here with a D. So domain, like I said, I can put in any single x value. It's a line that goes on left and right forever. So it's for all. So upside down A is for all. And then real numbers, an R with a double vertical line stands for real numbers. So I'll use these abbreviations here. So for my range of this function, again, it's going to go down and up forever. It's for all real. Sometimes we'll put for all real y's, for all real x's as well there. So B, x squared plus y squared equals 9. We know that this is going to be a circle with a center at 0, 0, and a radius equal to square root of 9 is 3. Well, notice if I have an x value equal to 0, I'm going to have a y value that's plus or minus 3. So I do not have a unique answer for my input of 0, so this is not a function. Okay, and I can look at this on my graph. If I present a graph of x squared plus y squared equals 9, again, you can see at 0 and many other places along this that does not pass the vertical line test. It crosses more than once. So part C, y squared equals x plus 2. Well, this looks like a parabola, but because the y is squared, it's a parabola facing off in this direction. Again, if I let x be equal to 2, I'm going to have y squared is equal to 4. Well, when I square root that, I get plus or minus 2. So I can see there is not a unique value for plugging in 2. So it's not a function. Again, if I graph that on a graphing utility, I can notice that sideways parabola, again, at 2 does not pass a vertical line test and many other places. And it might just have one solution here, but all we need is one spot on our graph that it doesn't pass the vertical line test. It is not a function. Our last one, y equals x minus 5. Well, I can always take the square root of a positive number, and I'm going to get a unique answer. I only get positive answers from this. So this is going to be a function. And with domains, I always want to be careful with dividing by 0 and taking a square root of a negative number. So here, I know if this ends up being negative, I will end up having a square root of a negative number, which then it will give me imaginary solutions. And we're not dealing with imaginary numbers here with functions. So what I want to do is I want to make sure that x minus 5 is greater than or equal to 0. So always take the argument underneath your radicand, set it greater than or equal to 0, and solve that out. So I get x's must be greater than or equal to 0. So this is a function, and my domain is going to be for all real x's greater than or equal to, add 5 to both sides, and I get 5 here, greater than equal to 5. Now my range values. So my range, I know I can't have negative numbers. It's a square root of something. So it's going to be for all real y's greater than or equal to 0. Again, I can graph this and Let's think of it visually. And I can see, yes, it does pass my vertical line test all the way through. And as I look at my domain, I can see that its x's greater than 2 going off in this direction. And I can see that for my range, its values greater than y going off in that direction. All right, so let's look at some function notation here. So the function is defined by f of x equals 3x minus 7. So don't think of these as parentheses in an operation, but as something new. Okay, we're not going to be multiplying f to x, but as functional notation. All it says is whatever you see here, plug it in for the x value there and evaluate. Okay, so for instance, if f of -2, I'm going to put -2 in everywhere I see x on the other side. I'm going to evaluate it for that function. So I get this is equal to -6 minus 7. That's equal to -13. All right, so if I want to do f of x plus f of 1, well, f of x, I can just substitute here is 3x minus 7. That's this first piece. The next piece is f of 1. So plus f of 1. So that's going to be 3. Instead of an x in there, it's going to be a 1 minus 7. So from here, I'm just going to simplify. So I get a plus 3 minus 7 and 3x minus 7. So minus 7 is minus 14. So I'm going to get 3x minus 11. Okay. So again, whatever's inside these parentheses, so now I have a larger expression, x plus 1, I just substituted it in again. So I do 3. Now where my x was, I put x plus 1 and plus or minus 7 here. Again, it's just coming from my function. And now I simplify it. I get 3x plus 3 minus 7, which simplifies to 3x minus 4. Okay. Well, if x is negative, I can do this is equal to 3 times negative x minus 7. And what I get is negative 3x minus 7. So notice it's still a function. It still needs an input of an x. Okay. Notice the differences here. Okay. So the negatives on the outside, I can just substitute in. Negative f of x is equal to 3x minus 7, and I distribute the negative through. And that's the answer there. If I want to find f of x equals 11, find x, well, I know that this piece here is equal to 3x minus 7. Set it equal to 11, so I'm just substituting in what I know about f of x. It's this. Find the x. Well, now I solve this out. I add 7 to both sides. I get 3x is equal to 18. And I get x is equal to 6. So I can say that f of 6 is equal to 11. All right. So last piece here. Find the domain for each of the following functions. So big thing with domain are big red flags that come up where we have issues. So red flag number 1. Don't divide by 0. Number 2, like we did before, your square roots, whatever the value this is, it has to be greater than or equal to 0. Otherwise, you're taking a square root of a negative number, and we don't want to deal with imaginary numbers here. So I look at g of x, and I want to find the domain. Well, my domains are only going to be an issue because I don't want to divide by 0. So I say, well, x minus 9 can't be equal to 0. And I just solve this just like it was equality. So x cannot be equal to 9. And by inspection, I can just say, well, yeah, if I plugged in 9, there would be 0. So the domain is for all real x's except x cannot be equal to 9. Okay. Now for h of x. Again, it's my radical. I don't want that piece to be negative, so it's got to be greater than or equal to 0. Subtract 6 from both sides to get x is greater than or equal to -6. So my domain is for all real x's greater than or equal to -6. All right. So for my last piece, well, the nice thing about a function that is a quadratic, I know it's a parabola that goes off to the left and right forever. Okay. I can do any x value I can plug in. You give me any number, I can square it and add 3 to it. So for this one, our domain is just simply for all real x's. All right, that concludes our notes for the evening. Make sure you highlight any questions you have and bring them to class tomorrow.